Hi, so we had an issue at the review session where we had to stop the recording in the middle of the session and start recording again. I had to wipe all the previous content. So after the fact, I'm just going through it right now and I'm going to try to do a quick review of slides 1 through 30 before we jump to the actual live recording. So this is an in-person notice. This is a disclaimer. I've tried to make all the information in this presentation as accurate as possible, but you can verify for yourself. I've left the sources for all information I put in these slides in the actual slide notes on the PowerPoint. So I'll also provide a link in the description of this video to download the original slides and also the slides with the annotations that I draw here. All right, so this is just an outline of some of the concepts we'll be covering. I think we're going to get maybe up to right about here in this recording, but we'll find out. So our first topic is KB agents. So these are knowledge-based agents, and they use a process of reasoning over an internal representation of knowledge to decide what actions to take. So basically, you give them a real-world scenario. They construct a representation of that real-world scenario on the inside. You feed them information from their environment in a language they can understand, and then they use some logic to give you actions that they can take in a language that they understand. So it's kind of like a simulation. And because the creatures that we best know for using knowledge and logic are ourselves, there's a lot of parallels to ourselves in these KB agents. So it's a perfect example to bring the real into the abstract. There's nothing more relatable than our own existence, after all. Of course, humans are not entirely logical, but yeah, that's a different topic. So there's 4 categories of components in a KB agent generally. So we have our knowledge base here. So this is like the human memory. We have our sensors. So this is how the KB learns about the environment around them. And we do the same with our 5 senses with touch, sight, smell, hearing, all that. Then there's actuators. These are the actions that the KB agent can take. So for us, we have our muscles and everything that we can control that allows us to make actions. For a KB agent, it's not typically that minute. So for instance, you can have a KB agent move or shoot an arrow, but it might not be necessary for a KB agent to have access to a whole series of of actuators for different muscles or things like that. But that would be necessary in like human modeled robots, which are pretty cool. And then of course the logic, cognitive functions, both the knowledge base and the logic are correlating with the human brain. So our first element is the knowledge base, which is a set of sentences. Now, of course, these aren't English language sentences necessarily, although they sort of serve the same purpose in that they're a unit of conveying information. So here we see an example knowledge base with only 2 sentences in it, and each sentence states a assertion or premise about the agent's world. So it's some information that they've either gathered through their sensors or been given beforehand by us. So for instance, this might be the start of a knowledge base for the Wumpus world example, where the agent knows that falling into a pit leads to them dying, and getting into the same space as the Wumpus will also lead to them dying. Of course, in the English language, our sentences are conveyed in a consistent language with consistent syntax, but computers aren't nearly, or at least at this level of type of agent, computers aren't nearly as good as detecting informal syntax or things like that. So we're going to use a formal language called a knowledge representation language. Of course, nowadays we have things like ChatGPT that can pick up what you're saying if you use some bad English or whatnot. But for these agents, they're pretty simple, so we need to stick with the formal language. So a little bit more on sentences. One special type of sentence is an axiom. So an axiom is a sentence that is not derived from any other sentence. So it's a fundamental, unchangeable truth. And sometimes the agent is also given background knowledge, like we were talking about with the knowledge base before. We might feed in some things in the beginning so that the agent doesn't need to learn everything just by going about its operations. And axioms typically are a part of the background knowledge, although that can depend on your specific agent. And just as a little note here, if it's not derived, what that means is that the sentence is not inferred or not derived from any pre-existing sentences. So it's kind of the start from which different sentences flow forth. So we have a couple different operations we can do with our sentences. We can tell an agent a sentence, which is like adding something to its memory, giving it more knowledge, or we can ask an agent a query, which is where we're giving an agent a query and we're asking, hey, gather all the information from the knowledge base that you have so far, and then go ahead and return us appropriate action for the environment that you're in, which is usually linked to time. Now, both of these operations may involve inference, which is deriving new sentences from old. Now, we're going to see this topic a lot in this chapter, and also know that inference should follow from the knowledge base. So, optimally, with inference, we're not making anything up. Inference should just be a new perspective or a realization from the knowledge that we already have. And we'll see an example of that later. But we're not trying to make anything new, just trying to detect a pattern in the knowledge we have. All right, so for humans, going back to our example, human axioms and background knowledge are questionable. That's more of a topic for religion or philosophy, but it's easy to tell something or ask something of a human, right? So when we see the world around us, when we experience things, when we interact with other people, when we have bad experiences, that enters our knowledge base, our memory, and that influences a lot of the actions that we're going to take in the future. So for instance, one experience that a lot of us have as kids is we are told by living that putting your hand on a hot stove is a bad idea because you burn your hand. And an ask is instead a reaction to something that happens, to new information that we calculate based off our KB. So when we get punched in the face, that's a reaction to stimuli. In that case, the human ask may not be 100% rational. Obviously, humans are a lot more complex, and we've got fight or flight and a whole other parts about us that is not just our brain. But just like humans, a KB agent's ask may be misguided by sensors. So for instance, all the information that we perceive, that might not be reality as it is, we have a lot of things, biases and conditions and things like that can stop us from experiencing reality truly as it is. And of course, human beings are largely declarative. There we go. And what is declarative? Well, a declarative approach is building an agent by telling it everything it needs to know. And a procedural approach is building an agent by encoding different behaviors as program code. So a declarative approach will say, okay, here's all the rules regarding how to face east. So if you're looking north, then you can face east by turning to the right by 90 degrees. If you're facing west, you can turn to the east by turning right by 180 degrees, so on and so forth. Whereas a procedural approach says, oh, okay, you want to face east? Well, let's gather some information about where you're at right now. Let's see, you're facing north. Okay, so then you'll have to turn right by 90. Or, oh, let's see, you're facing east right now. Well, then I guess we'll go ahead and execute that turn right by 90 twice. And you can do that again. You can see how you do the else, and you could turn left by 90 and so on and so forth. So that being the case, procedural obviously is a little bit faster. your agent kind of has a mapping. If it wants to do one action, it has a function for that. And so you can just go through an if statement, which is pretty fast. Whereas with a declarative approach, that can be pretty slow, because if your agent wants to face east, then it's going to have to sort through the entirety of its knowledge base, see all the rules that are applicable to facing east, gather those together, evaluate its current state, and then take the appropriate action. So that's a little difficult. So successful agents often combine both elements in their design. Obviously, we don't want static agents that can't react to new things happening in their environment. So we'll need to combine both. But it is good to know that declarative knowledge can be reduced into more efficient procedural code. So we can take a bunch of related declarative operations and we can translate it into this procedural code that we see here. Now, there's a couple of different perspectives on knowledge, right? So the knowledge level is what the agent knows regardless of implementation. So this is something like an exam or a quiz, like the SAT, where it's just trying to gather, hey, what do you know? And can you work with this knowledge? And meanwhile, the implementation level is the data structures representing the KB and the algorithms that manipulate them. So this, in the knowledge level, in this sort of examination, we're not asking, oh, did you memorize using flashcards, or are you a visual learner or an auditory learner? Whereas an implementation level is getting kind of down into the details there. Another way to think about this is software engineering, for instance. So in software engineering, you have a design and implementation phase, where a design is just like a general level instruction, and then implementation is, okay, exactly how are we going to do this? What tools are we going to use this? Or, a manager and employee, manager says, hey, go dig this tunnel. The employees figure out, how do we do this safe? What tools to do this? Are we going to need to schedule things or close off roads and all these other points of implementation? So broad scope to small scope. So not only do we have all of our memory, we also have sensors, right? So the KB agent uses its sensors to learn more about the world around it. Just like we have our different senses that we talked about, KB receives information through the sensors. However, the KB receives this information through its KRL, which is its knowledge representation language. So taking informal sensor data, translating it into a language that the KB agent can understand. And like I said earlier, these sensors can be deceived based off an incomplete understanding of what's happening. And we'll actually have an example for that later. So this is a pop quiz. This would work a little bit better in person, but yes, a KRL is a knowledge representation language. Now, KB can not only sense what's going on in the world, but of course it can also act on it, right? So a KB agent takes actions in the world through actuators. We're talking in Wumpus world, shoot the bow, move, turn, pick up the gold, go up the ladder, things like that. So actions are generally tightly linked with the passage of time, right? So when we take an action, time moves forward, and then that gives us a new perception to feed into the KB agent, and then we create an action for that, and then we do the action, and time moves forward, and the cycle continues. Now note that actions can be associated with prerequisites or costs. So for instance, in Wumpus World, when we shoot the arrow, that uses the arrow resource, and if we use the arrow resource, we can't shoot again. Or just like writing, you need to have pencil, paper, and energy, and maybe some caffeine to get done with a lot of writing. While actions can have prerequisites or costs, so things to do them, we can also do an evaluation of after we do them. We can have a performance measure, a punishment reward system you might have heard. So for instance, in Wumpus World, you get a heavy reward plus 1,000 if you get the gold. But if you die, you fall in a pit, or you get eaten by the Wumpus, it's a heavy punishment. So that's a minus 1,000 performance measure. So that's pretty heavy. And just as a little note here about actions in general, a KB agent in a static world that's single agent, maybe it knows what it needs to do from the start, just can't execute it all at one time due to action cost. But the KB agent basically always knows what the right thing to do is. Kind of like Minimax with the game search that we went over. But in a multi-agent system, or in a system where the environment is not static or not fully observable, an agent, what is the optimal action, could really change from action to action as time progresses. So just something to keep in mind. And finally, logic as the last component of the KB. Now, we're going to talk about this a lot more, so I'm not going to elaborate on it too much right now. But for now, know that logic decides how KB agent responds to an ask based on its knowledge base. As we said, actions are executed with the agent's actuators. And as a small side note, when an agent draws a conclusion from correct information, that conclusion is guaranteed to be correct. So we're not talking about irrational agents like humans. We're just talking in this context that when an agent draws a conclusion from correct information, the conclusion is guaranteed to be correct. And it's also probably worth noting that in this chapter, most of the agents or scenarios that we're working with, there's not a chance of receiving faulty or incorrect information. All right, so this is our basic KB agent, right? So our input parameter is a percept, which stands for perception, right? So this is basically the collection of all the agent is perceiving from its sensors. So we had an example of this with Wumpus World where you had none, none, and then you had, maybe you detect breeze here, so on and so forth. So what we do is we translate that perception into the knowledge representation language, and then we feed that in to the KB. We tell that to the agent. We tell that to the knowledge base. Then what we do is, and note that all of these operations are linked to time, and then we ask the KB, we say, all right, so having understood what just happened at time t, what action would you like to do to respond to the scenario at time t? So that gives us an action. Now, of course, the KB is the agent's perception of reality, right? So if at this point, the KB doesn't actually know what it did. So what we do is we translate that action into the knowledge representation language, and then again, and I'm going to use a different color so maybe it's a bit easier to see, and we're going to feed that back into the KB, into the knowledge base, right? And then we're going to, like I said, actions are highly associated with let's do that, highly associated with passage of time. So we pass time forward, return that action. So this is all we need, obviously. The nuts and bolts of tell, ask, make percept, sentence, make action, query, that's where the real magic happens, but this is technically a full KB agent pseudocode. All right, so this is our Wumpus World example that we saw in class, and I'm not going to go into too much detail on this, seeing as it's been covered extensively in class, but you can see this is the performance measure, so how each action is evaluated, what the KB agent can do, what it can sense, and different characteristics about the environment. So you can reference the slides in the book for more detail on this. One thing that I do want to point out is IFF, that is not a typo. IFF means if and only if. That will be used continually throughout this chapter. This is something I did not know going into this chapter, so I'm telling you that now because I didn't. Maybe you did, and if so, good for you, but that's what that means. So a couple characteristics of Wumpus World, right? These are some of the metrics that we use to evaluate or describe any given simulation, or maybe world rather. And so here are some of the values for Wumpus World. So first, is it observable? Well, no, not fully. We only have local perception. The agent can only see within one space, so no. Wumpus World is not observable. Deterministic? Yes. Outcomes are exactly as specified. There's no random chance, unpredictability. There's no way for Wumpus World to act or change in any way that we don't expect. Episodic, no. So what episodic means is basically non-sequential. So each world of Wumpus World, or each simulation, if you will, is given to the agent who makes an action, and then after that, it's a completely different world or simulation. One action doesn't follow up to another action. There's not a sequential chain of events or passage of time. You're just given one instance, you evaluate, and then you move to the next completely disconnected instance. So, whoops. That is the wrong marker. There we go. So no, Wumpus World is not episodic. Instead, it is sequential. Sequential. All right, so is it static? Yes. Nothing about the environment moves. The Wumpus doesn't move. The pits don't move. This is another area where the KB agent, its optimal action would change as its environment changed, but because it is static, that helps the agent predict what's going to happen as Wumpus World moves forward in time. So discrete, yes. There's a defined number of spaces and a defined method of navigating them. You know, this is not like continuous state spaces that we covered in search algorithms. This is not like walking around on campus where you can walk in any direction and, you know, infinitely many bearings at infinitely many distances and infinite number of spaces and things like that. At least effectively infinite. This is just a defined number of spaces, defined method of navigation. And finally, it is single agent. The KB agent, the explorer, if you will, is the only one interacting with the environment. The Wumpus, you know, if it was a part of the environment and it moved, you know, maybe in a sequential or normative pattern, it would be not static but still single agent. But you know, you could have a case where the Wumpus is another KB agent, for instance, with its own goals to try to hunt down the explorer. And in that case, it would be multiple agent, but no other agents take turns or actions. Okay, and unfortunately, I can't answer your questions over video, although you can certainly send me an email or a message. All right, so now we can jump into logic, thinking about thinking. So just an introduction to logic. Logics are formal languages for representing information such that conclusions can be drawn. So setting something we all agree on so that we can operate on different sentences and draw conclusions. So syntax defines how sentences in the language are expressed. This consistent syntax makes it much easier for a computer to process or work with a formal language, right? And semantics define the meaning of sentences. So if I wanted to write this is a perfectly valid sentence in propositional logic, but if you don't have the semantics, you don't know what it means. It can be correct and it can be called something. It can be called A and B, but you don't know what A and B implies. That's when we get into the realm of truth tables and semantics and things like that. So semantics define the truth of each sentence with respect to each possible world. You can think of a possible world kind of like a possible state for the simulation. It's also maybe not as tightly defined as a model, which we'll get to later, so it's kind of flexible, but basically defining, is a sentence true in a certain context? And every sentence must be either true or false, so Boolean values, 1 or 0. Except in fuzzy logic where you have truth on a scale, but that's a different topic for chapter 13 if you want to check it out. So moving on, one logic language that hopefully you're familiar with is arithmetic, right? So you have X, which is a propositional symbol, plus, which is a logical connector, Y, which is another propositional symbol, connector, and a value. So we recognize that this is a valid sentence of arithmetic. Meanwhile, x4y plus equals nothing is not. Then we have x plus 2 is greater than or equal to y is true if and only if. Remember, the number x plus 2 is no less than the number y. And there's just some other examples here, but you see how arithmetic can form sentences and have truth values and variables and all these other things. Now we're going to talk about models, as I was saying. A possible world you might be able to assign x and y as anything, right? So, you could have x be a float, negative float, and your x value is, let's just switch to a pen for this, negative, switch there, negative 0.8, and your y value is 2.3. And that could be a valid possible world, but not exactly easy for a computer to work with, right? If you could just assign x and y to anything, x equals a and y equals b, or x equals dog and y equals cat, then you really don't have any meaningful way to verify if x plus y equals 4. But a model constrains the assignment of those variables to values that we know how to work with. So, we could constrain the non-negative integer values for x and y, so that x would have to be something reasonable like 2 and y is equal to 1. It still doesn't make the sentence true, but it's at least a lot easier to work with, at least for a computer. Moving on, a model. It's a formal definition is that a model is a mathematical abstraction where every relevant sentence has a fixed truth value. So basically, it's kind of like a state where we're assigning a value to every variable, where a variable is a propositional symbol. And we could, talk about how model 1 equals x equals 2 and y equals 2, and model 1 satisfies whatever this sentence is called, which is using some future terminology we'll get into. Oh, it's right here. Okay, so the sentence alpha is true in model M. We say that M satisfies alpha, or sometimes M is a model of alpha. So in this case, we say the model satisfies alpha if alpha is x plus y equals 4, right? And then M of alpha just means the set of all models of alpha. So every model that can satisfy alpha is going to be within M of alpha. And so for this x and y example, we've got 1 and 3 is within M of A. For our assignments, we've got 2, 2, 3, 1, so on and so forth. There's going to be, I think, there's going to be a lot of those. Well, our model is non-negative integer, so we're going to be limited, but there are going to be a couple of those. All right, entailment, right? So entailment is the idea that a sentence follows logically from another sentence. So basically, it's saying if I have a sentence alpha that is true, then the sentence beta is true, and we use this notation for that. So the formal definition, how we actually represent that within our logic, is that A entails B, if and only if, every model in which alpha is true, beta is also true. And then we have some good set notation right here for that, saying all the models of alpha must be a subset of all the models of beta. So this also means that A is typically a stronger assertion than B, right? Or alpha is typically a stronger assertion than beta. Because the set of models of alpha is typically smaller than the set of models of beta. And if the set of models of alpha was equal to the set of models of beta, then those two sentences would be logically equivalent, which we'll get to soon. But we have an example here. So let's say we have a sentence alpha is x equals 0, and a sentence beta xy equals 0, right? So in all the cases where alpha is true, then beta is also true, right? Because 0 times anything is 0. So y could be any value, and alpha would still hold, right? But beta, you can see, is a bit more of a broad set of models, right? Because, let's say we have x is equal to 2 and y is equal to 0. That's a model that isn't in alpha. It's not compatible with alpha. It doesn't satisfy alpha. But it's still a model within the set of models of beta. So just something to keep in mind there. that it's a stronger assertion here. Okay, so we're reaching to the end of this home recorded segment, but we end off at slide 30, so I guess I'll do 27 through 29. So now we're going to visualize entailment, right? It's a very important pivotal concept, so we want to make sure that we get it right. So this red set here is the knowledge base. And you can think of the knowledge base as kind of the summary of all possible models of reality, right? Because the knowledge base is everything that the agent has perceived about reality. So really anything outside of the knowledge base can't be real, at least in an environment where all the information is reliable and static and so on and so forth. So that leads us to, some pretty easy inferences regarding other scenarios. So let's say we have a sentence A equals the space 1, 2 is safe, right? And I think that should be, I'm not exactly seeing what space that would be. Oh, right. Here we are. So 1, 2 is the space. So all models where 1, 2 is safe. So we see that all of the models of the knowledge base are also models of A. So that means that basically A is consistent with every possible reality. Now as the knowledge base shrinks, we'll find which of these models is actually real. But as knowledge base shrinks, that doesn't change entailment, right? So because entailment involves having more models than the stricter sentence. So as knowledge base shrinks, the entailment will continue to be true. But just for now, as we have multiple models that fit in our knowledge base, we know that the knowledge base entails A, because in all of the models of knowledge base, in all of the models of the knowledge base, they are also models of A. And that looks like where we're going to pass off to future me, or past me, rather. See you there. So now this is a different constraint, or this is a different sentence, rather, B. So the sentence B says that the state 2, 2 is safe. Now, B is not true in all models of the knowledge base. So basically, B is not true in every reality that we know of. So B could be true, but it also might not be true. So we don't say that the knowledge base entails B. It doesn't. But let's consider a case where a new perception, O, changes the knowledge base. Like let's say the agent moves, and so it discovers something else about the world. So in that case, we have one of two options. So let's call the state that's boxed in the purple here, call that S. So if this new observation O removes S from the knowledge base, so we have our new knowledge base now here that is boxed in the red, then we know that B is not true because there's no overlap between the two sets anymore. Basically we know that B is not true because all of the sets where B is true are completely different than all of the sets that we know to be reality. So B has been proven false. But alternatively, let's say that observation O instead makes it to where S is the only state in the knowledge base. So this could very easily be the case where we learn that there's not a pit at 2, 2. Then in that case, we know, B being that 2, 2 is safe. The knowledge base has shrunk to only include this one state, which is fully inside the set of models that align with B. So now we know that the knowledge base entails B, that B is true. So those are the ways that different sentences that the knowledge base doesn't entail may prove to actually end up, like KB could end up entailing a sentence that it might not have been able to before. So does that make sense? All right, cool. All right. So entailment can be applied to derive conclusions, that is to carry out logical inference. The prior example being model checking, because we're enumerating through all the possible models to verify entailment. So model checking just enumerating through everything is not smart in any way. We're looking at O of 2 to the n complexity. We're just doing a shotgun blast, seeing if we find what's right. Okay, so now we're going to talk about inference in more formal terms. So KB infers alpha. So that means a sentence alpha can be derived from KB by the inference algorithm I. So an inference algorithm I is searching for a consequence or additional truth that's implied by KB, and alpha is the result. So again, we're not trying to come up with something new or false that's not based on existing information. We're just trying to conclude a more precise, more insightful truth from all the things that we know. So a simple example here, let's say we know that x equals to 2, y is equal to 2, and 2 plus 2 equals 4. So we run an inference algorithm on it, and we may prove that x plus y equals 4. This is something that's more insightful than some of the knowledge that we had before that infers from knowledge that we know to be true. So there's a couple of characteristics of inference algorithms. So if an inference algorithm is sound, that means that the inference algorithm doesn't make anything up. If it comes up with a sentence A, then the knowledge base must entail A. Completeness, it means that the inference algorithm can infer any sentence that is entailed by the knowledge base. So that means if the knowledge base entails a sentence, that the inference algorithm can always devise it, that the inference algorithm is not going to miss any sort of sentences. And both properties are very highly desirable. We don't want our inference algorithm to be messing up, and we also don't want it to be getting an incomplete look at all the observations we can make from a knowledge base. So there's just a chart here. Basically, we have a really bad algorithm here that can't infer everything it entails and may infer false sentences, and then the best case is where our algorithm is both complete and sound. So one final note is grounding. Grounding is the connection between what the KB agent observes and what's actually in the real world. So anytime we're making a knowledge base, or anytime we're making a simulation, or setting up these sentences and sensors and actuators and things like that, all we're trying to do is represent a real situation. And so grounding is the concept of what's the actual match between what the KB agent is interacting with and what it's doing, and what is the actual real world or real situation that it's in. So even with perfect sensors and translation, a problem arises when a KB agent is learning. So if we have a robot that observes the sky and it says, okay, the sun is always, so the sun can be in the sky, the moon can be in the sky, and they are never in the sky at the same time. The robot would be right on that assumption or that sentence for like 99% of the time. But the moment you throw in a lunar eclipse, the robot is completely wrong and it has no idea what's going on because the moon is in front of the sun. What's happening? So a lot of KB agents that we deploy in the real world, they're learning like this. They're basically making inferences from the data that they see. But when anomalies come up, their sentences, their knowledge base becomes inaccurate. And so we have to adapt and we have to plan for that. So that's enough about regular logic. So now we'll jump into propositional logic, which is the first class of logic that we're going to be doing. We get into first order logic later, but right now we're just talking propositional. It's the simplest logic. Its core unit are proposition symbols. So that's basically, the way I like to think about it is variables, right? So pit at 1, 1 is a proposition symbol, and it's a variable that you can assign with the value true or false. An atomic sentence is a sentence that just contains a single proposition symbol. Atomic sentence is different from a literal. So an atomic sentence is just a symbol, whereas a literal, it might have the not operator on a single proposition symbol. And then, of course, complex sentences you can form by connecting simple sentences using parentheses and operators called logical connectives. So this is a look at the propositional logic syntax tree. We have an atomic sentence, with just a proposition symbol, we have the AND operator that is connecting the two. Then we have another complex sentence that is nested inside of the original, which is each made of its own single propositional symbol connected with the logical connective. So our first connective is not. This is just going to do the negation of a proposition symbol. And a literal is either an atomic sentence or a negated atomic sentence. So a positive literal or a negative literal. So this is a positive literal and this is a negative literal. And you can see it just flips the value. The AND connective is just, it's doing a conjunction. It's basically checking if both of the parts are true. That's the only case in which the AND yields a true, is if both conjuncts are true. Anywhere else it'll be false. And of course, to remember this, there's the AND operator and the A and AND have a very similar look. Next is OR. This is called a disjunction, and its parts are disjuncts. So if the two disjuncts are anything other than false, false, then it's going to be true. So if it's false or true, true or false, true, true, then it's going to return true. Just saying, are any of these disjuncts true? Then we have implies. So this relationship is called an implication or a conditional. The first sentence, the one that goes before the actual implies symbol, we're going to call that the premise or antecedent. I typically use the latter. And then the sentence that comes after the symbol is the conclusion or consequent. So implications are also known as rules or if-then statements. The reason behind that is because if it's false, that's like the parameter in an if statement is false, right? It doesn't matter. We don't care at that point. We just skip. So we call it true. But if the premise is true and the conclusion is false, then we know that the premise does not imply the conclusion, so we say it's false. But if the premise is true and the conclusion is true, then we say that the premise implies the conclusion and it's true. So it's true in all cases except where the premise is true and the conclusion is false. And then the last is if and only if, which is called the biconditional. A more technical definition is that P implies Q and Q implies P. To me, it's most easy to think as equality, but they're not technically the same. So false and false is true, true and true is true, but if they have different values, then they're going to be false. And this is just a truth table. And if we have the values P and Q, what are the status of all those? You can look over those later if you'd like as a reference. So in propositional logic, a model simply sets the truth value for every propositional symbol. So we're assigning every variable. So pit at 1, 2 is false, pit at 2, 2 is false, pit at 3, 1 is true. So a sentence can be applied to our models. So let's say we have a sentence where there has to be a pit at 1, 2 or a pit at 3, 1. This would be true in our model because pit 3, 1 is true right here. But if we had the sentence pit in the space 1, 2 or pit in the space 2, 2, this sentence would be false in this model because both of these values are false. So with that, we can just go ahead and construct our first inference algorithm. So just to set up, I'm going to go into the steps and then show you the inference by enumeration table. But let's just say we've got a bunch of proposition symbols, P of I, a set of sentences, S of I. So you could think of these as variables or constraints in constraint satisfaction problems. So sentences are bounds on our proposition symbols. And then the KB contains all sentences, S of I. And then we're going to say we have a sentence alpha that is in terms of our different variables. So this sentence may or may not be in the knowledge base. We don't know. Or it may or may not be entailed by the knowledge base, more accurately. So for our very primitive inference algorithm, we're just going to enumerate through all possible models. We're going to test all of them against the knowledge base, only keeping those where the knowledge base is true. And then we're going to check if alpha holds for all models where KB is true. And then if alpha holds for all models where KB is true, then we know that KB entails alpha. Again, we don't care because this is an entailment relationship. We don't care if the model is false in KB and true in alpha. That doesn't help us in any way. Typically, that will be the case for a bunch of models because the model set of alpha is typically larger than the model set of the knowledge base, but we don't care. So this is the truth table for inference. So each row, except for the header, is a possible model. We see our proposition symbols are like our variables. And so we're going to keep changing those until we iterate through all possible combinations of the proposition symbols. And then our sentences, these are like our constraints here. Basically, these will either be true or false depending on our different proposition symbols. Each of these sentences is going to be a part of KB. So this is all of the sentences that are a part of KB. So for all of those sentences must be true for KB to be true. And then we would harvest these or store these three models where KB is true, and then we'd check to see if alpha is true in all of these. And if so, then KB entails alpha. Are there any questions about this method of inference? Yeah.
So if you do the entailment and it's true, right, like it actually entails, then you could add an S6 column there and then put that new sentence in?
Correct. Yeah, so you could turn alpha into S of 6 if you'd like. Which would not, because alpha is a more broad constraint than the knowledge base, that wouldn't actually change the knowledge base at all, but you could do it. Because remember, this is an inference. We're basically coming up with things that are already true about the knowledge base. But yes, we can add that back in, which could be useful for some other algorithm. So inference by enumeration is sound and complete. These are our highly desirable quantities, but the problem is that it sucks because the time complexity is 2 to the power of n, and it does not do anything to reduce this. Because the problem of propositional entailment is co-NP complete, we can't reduce our worst complexity from 2 to the n, but we can do a bunch of different strategies to try to scale back that complexity. So now we're going to move on to entailment concepts and inference rules. This is just the predecessor to be able to do advanced inference algorithms like backchaining or forward chaining or stuff like that. So we're going to need a couple of logical tools before we go into it. We're going to be doing some theorem proving, but we're going to need the ideas of logical equivalence, validity, and satisfiability. So the first is logical equivalent. We're going to claim that two sentences are logically equivalent if and only if they're true in the same models. So a sentence alpha is logically equivalent to a sentence beta if the sentence alpha entails beta and if the sentence beta entails alpha. And this property is pretty kind of apparent. There's not too much explanation that needs to be done there. But this allows a bunch of logical equivalencies to be applied to our sentences instead of just booleans. So a sentence, we say, is valid if it is true in all models. Valid sentences are also called tautologies, and they're necessarily true. So no matter what the truth value of A is, we know that this sentence is going to be true. So across all models, across all possible configurations of all variables, this will always be true. So validity is connected to inference via the deduction theorem. So for any sentences alpha and beta, alpha entails beta if and only if the sentence alpha implies beta is valid. So this is the false always leads to true sort of relationship. So does that deduction theorem make sense to everyone? Does everyone understand like why that is? Okay, cool. Yeah, so you can check back in the slides later if you want a more further explanation, but basically we're just saying that that truth table that we saw for the implication is equivalent to the truth table that would be drawn by entailment. So a sentence is satisfiable if it is true in some model, and a sentence is unsatisfiable if it is true in no models. So if there's any case where the sentence can be true, it's going to be satisfiable. Any case where the sentence will never be true. So if the sentence is never true, unsatisfiable. And we say that if A entails B, or if alpha entails beta, then alpha conjoined with the negation of beta is unsatisfiable. So alpha and the opposite of beta can never be true. So this is a proof by refutation or a proof by contradiction, which we'll see once we get to resolution. But does satisfiability make sense? Okay, cool. So we'll also take a quick detour into inference rules, just one slide. All you need to know, one applies inference rules to derive a proof, which is just the series of logical steps to get to a desired goal. And we're going to use this notation where if sentence 1 is true and sentence 2 is true, then sentence 3 is also true. Another form of this notation just has sentence 1 and sentence 3. So sentence 1 is true, then sentence 3 is true. The two rules are modus ponens and elimination. So if A implies B is true and A is true, then B must be true. We understand that from the truth table of implication. And then and elimination just says if A and B is true, then A must be true, because of course both values of that statement must be true for A and B to be true. And you could also swap this out with B and it'd still be true. And there's more practice for that in the book. I'd recommend going through that. You can revisit that later if you want more exercise with proofs.
So for the modus ponens, is that when it says states those variables on the right, that means that that evaluates the true?
Yeah, so the two sentences, which they don't have to be just propositional symbols, but the two sentences, like A implies B and alpha are both true, is what it's saying at the top.
So if you were to have like the CNF form and you have two clauses, both those have to evaluate the true in order for you to use modus ponens?
Yeah, so you could do something like this, where alpha and beta, comma, beta and C. So you would basically be saying, okay, alpha and beta is true, which means A and B are both true. B and C is true, so B and C are both true, and from there you could derive A, B, or C. So that's just conjunctive normal form, or I guess, so with CNF you would be doing that, I think. In which case, you couldn't necessarily infer anything from that, because if A is true and C is true, then B could be false. If B is true, then both of those would be true. So you can't really infer anything from that statement. But
so if you were to do the CNF, so could you write any simplification of that, or at this point would you just say that the proof by contradiction would just terminate?
I don't think there's anything to be derived from these statements. I don't think they can be simplified further, if that's what you mean.
Yeah, because, okay, so you're saying.
Because the only thing you would know is that A or B is true and B or C is true. Okay, so for our inference algorithms, we have two broad categories: application of inference rules. So this is kind of like a smarter sort of inference where we're using these different rules of logic to perform inference. We're not iterating through everything. Oops, there we go. Not iterating through everything. This typically requires a translation of sentences into a normal form, like we'll see coming up soon, like transforming all of our clauses into definite clauses or things like that. So this is going to have resolution, forward, and backward chaining, whereas our model checking, that's like our inference by enumeration that we just saw with the table. And there's also kind of smarter ways to do this to cut down on the amount of time we're using, like backtracking from the Australia example. or DPLL, which we'll get into. So for forward and backward chaining, we're going to need to have our clauses in horn form. So horn form just means that our knowledge base is a conjugation of horn clauses, so they're joined by our and a horn clause is either just the proposition symbol, so just the variable, in which case it's called a fact, or it's a conjugation of symbols called the body, and then a symbol called the head. So you can think of that as like, you could have any number of symbols here, A and B, a conjunction, symbols implied by the head C. I like to think of it as a caterpillar with the body because you can have as many symbols as you want here, but there's only one symbol in the head. And not all logical sentences can be expressed as a horn form. So this is another one of the syntax trees. We've got a horn clause. This is a fact, so just a C. We have a horn clause here with our conjugation of symbols. So this is the head, or sorry, this is the body actually. So we have the body, head, body, head. So a lot of flexibility with those horn clauses. Another relationship here is definite clauses, which actually we'll get into as we look to this next stuff. So can a horn clause be represented with any other connectives than just implies and conjunction and? No? Okay, so there is an alternate using our implication elimination and De Morgan's laws, so using our logical equivalency rules, we can actually express horn clause in a different expression. You can see through a couple of operations here, we turn all of those implications into uses of the not operator and use of the or operator. This is actually the most standard representation of horn clause in like other books and literature and courses. In this book, it seems to be one of the few that actually uses the implies operator. So this is also pretty similar to the definition for definite clauses, whereas definite clauses are basically these, but there must be one positive literal. So here this is a definite clause, this is a definite clause, this is a definite clause, because they all have a positive literal. So in this case it's B, A, and C. But if this B was a not B, then we would have, it would just be a horn clause, not a definite clause, because it doesn't have any positive literals. So the rule for a horn clause is that it's at most one positive literal, or for a definite clause it must have one positive literal. Okay. So we can now apply modus ponens to the horn form, and this algorithm is pretty cool because we can use it with forward chaining or backward chaining, and it also runs in linear time, which is nice because a lot of the stuff that we're doing here is exponential. So we're just saying, hey, if all of these sentences are true and all of these sentences imply beta, then beta is also true. And another perspective is to look at that as our knowledge base. It's inference, basically, is what we're describing. So now we get into forward chaining. So forward chaining just determines if a single propositional symbol is entailed by a knowledge base of definite clauses. So this query is not a sentence. It's just one symbol. So we're starting from known facts, which are positive literals, so just other proposition symbols that are in the knowledge base. And we can prove that this symbol is true in the knowledge base by starting with true symbols and traversing the different horn clauses to basically justify our conclusion. So this is our algorithm. We know that every sentence in this knowledge base is an implication or a positive literal because it's in horn form, so all the sentences are horn clauses. So that's why we're saying for each horn clause, not just each sentence. And we could walk through this algorithm, but we'll just do it here. So each of these sentences or clauses is going to have a counter based off of how many literals make them up. So for L and M, we have 2. For B and L, we have 2. For P implies Q, we only have 1. For A and P implies L, we have 2. For A and B implies L, we have 2. And then we start with the true literals, the things that we know for sure, which is A and B. And so this uses a Q-based implementation. So this is currently in the queue, in the queue. So we're going to pop A from the queue. And we do that so we know that A is true. We look at everything that uses A and its justification. So we have A and P. We reduce that to 1 because we know that A is true. And then we have A and B implies L. And we drop that to 1 because we know that A is true. So right now we have nothing else in the queue. Then we pop B from the queue. And we do that. We have A and B implies L. So that has dropped to 0. So now we know that A and B are true. So we know that L is true with that implication relationship. So we can add L to the queue of things that we need to look at. And then also B and L implies M. So we'll drop that counter to 1. So now we process L. And okay, let's see, what else do we have? B and L implies M. So we drop that counter. That drops to 0, which means that M is true. So we add that to the queue. And we have L and M implies P. Drop that to 1. Then we process M, pop it from the queue. And we see L and M implies P. Drop that to 0. Then we add P to the queue. Now we know that P is true. Now we visit P, pop it from the queue. We see that A and P, that implies L, so we would add L to the queue, but we see that L is already visited. And then we see that P implies Q has dropped to 0, meaning that Q has been proven. Any questions? All right, cool. So there's a whole proof of completeness on this. You can go through that. It's in the book. It's also in the slides. Basically just saying that we can entail every possible propositional symbol using forward chaining, but that's a whole thing. Then we have backward chaining, which is like forward chaining, but we're just working backwards from something, some premise that we already want to find, instead of just starting from the true literals and kind of seeing what we can imply. So there's a couple different measures here that are done to avoid repetition and loops. The first step of the algorithm is to see if Q is known already, and if so, we stop. But if not, then we have to prove all premises of some clause concluding with Q. So this being the case, we start with Q. We have a stack of things that are visited. So we visit Q, and then we see that P implies Q. So we visit P. And then P is involved with this one right here. So we see P implies.
You have to go to M and L first, right?
Yeah, so we take a look at M and L. And then
you have to go to the things that are composed of M and L, right?
Yeah, so there's a weird. I want to double check myself on this because it gets a little bit weird with the visitation order.
Did you have an example of this in the slides, like natural trace with back chaining?
Yeah, so you can check the example in his slides as well. There we go. So we know that A and B are true. We'll do that with a green circle there. Know that A and B are true. So we're going to visit L and M, and then we see that a justification for L is P and A. So we're going to visit A, but we know that A is true, so we know that now. And then with L, we're considering A and B implies L. So we visit A and B, and we see that A and B are true. So because we know that A and B are true, we start to traverse back up. We know that L is true. But one of the clauses that involves L is L and B implies M. So we go back up the ladder, kind of going through our visitation stack. So with M, we visit the L and B edge, and we see that L and B are true. So that means that M is true. We see with P that it has a clause where M and L are true, and we know that L and M are true because we already found that. So we know that P is true, which just leaves Q, and we know that Q is true. So we're going back down, basically, finding the true literals that justify the sentences and clauses that help us get there. So we're going down, we're finding the things that justify, and then we're walking back up through our visitation queue to see if Q is true. If B is false here, then we understand that basically this whole tree is wrong and that Q is not justified. But it is, A and B are true, so everything's justified there.
So once you get down to A and B, does it basically just turn into forward chaining, but directed towards Q?
Well, you walk back up the ones that you visited, and then you also have M in the tree. The thing with forward chaining is that with forward chaining you kind of just explore everywhere, right? So if you had a bunch of other clauses in this direction and this direction, you would end up exploring those too. Backward chaining basically only requires that you visit through the clauses that help you prove this node Q.
So it's like recursive. You go to Q and then you go to every literal that makes up, then you go to P and then you go to every literal. Yeah, that's the stack that makes up P, and then you just keep doing that until you reach a point where you can't add any more. Then the recursive calls kind of stop and you just work your way back up to Q, right?
Yeah, so basically you're adding, a more simple way to put it is that you're adding all the clauses until you get to the point where all of your clauses are just justified by true literals that you know are true. And then from there you start going back through all of the clauses, ensuring that it's true along every step of the way until you return back up. So in forward chaining, let's say you had 3 other true literals here, you would start there and you would explore all the way up their tree. But that's not necessary here because we're trying to prove Q from Q, so we're going down. We're not trying to infer Q by just looking at all the data we ever have and then seeing if that all leads to Q, right? So both are actually linear time complexity, but because backchaining targets that one section of the knowledge base, it's going to end up being much less by way of size. This is because backward chaining is goal driven. Basically, you're saying, hey, I want to prove this. How do we get there? Whereas forward chaining is just saying, this is everything I know is true for sure. What can I imply because of that? And then our last couple of topics are resolution, which is both an inference rule and an algorithm. Basically, resolution just takes in sentences that are in conjunctive normal form, and it's saying, hey, if we have any that are complementary, basically any that are conflicting, and we have 2 sentences that are in CNF form, then we can go ahead and just disjunct those sentences, so using the or symbol, but with those complementary literals removed. So you have an example right here where we have A or B or C, which is conjoined with D or not B or F. And then we pluck out B, and now we just have A or C or D or F. So that gives us an algorithm where basically we're recursing through all of our CNF sentences and we're resolving. So we're taking a look at all of these complementary literals, and we're saying, okay, we're removing all of those, and then we're bringing those 2 together into their own clauses. You can only do this with 2 clauses at a time. You can't do multiple. So you just keep going until you possibly get down to the empty set. So this is another proof by absurdum or proof by reduction type thing, where we're trying to conjoin KB with the inverse of the sentence that we're trying to prove. KB joined with the inverse of alpha. And so if we do resolution and we resolve all of our sentences in the knowledge base to the point where there's an empty set, that means that there's no justification where the inverse of alpha is true. So the inverse of alpha is unsatisfiable, which means that alpha itself is satisfiable. So KB joined with regular alpha is true. But if we're trying to resolve, but we can't resolve any further, we only just have a set of clauses, and that means there's a case where KB and not alpha is satisfiable. So that means that alpha is not true. So KB does not infer alpha. And then the last thing is DPLL. This is a smart model checking algorithm, and we can run through that with an example if you guys like, or we could run through an example with resolution as well, or both. But other than that, that is it.
Thank you,
So, yeah, are there any questions? I can stop the recording.